Welcome back to Midnight Science, where we embark on a gentle journey through the wonders of the universe, designed to soothe your mind and help you drift into peaceful sleep. Tonight, let's begin by unraveling the mysterious concept of space-time, that elegant tapestry woven from the threads of space and time, which physicists like me find endlessly fascinating. Imagine, if you will, space as the vast, open canvas where stars and galaxies dance, and time as the quiet river that flows through it all, carrying moments from past to future. In the early 20th century, Albert Einstein revolutionized our understanding with his theory of relativity, showing that space and time are not separate entities but intertwined in a single, flexible framework. This idea might sound abstract at first, but think of it like a soft, stretchy bedsheet. When you place a heavy object on it, the sheet dips and curves, altering the path of anything nearby. That is how massive objects, like stars or planets, warp space-time around them, guiding the motion of everything else in the universe. As we ease into this exploration, you will find yourself relaxing into the beauty of it all, feeling the gentle pull of gravity, not as a force, but as the subtle bend in this cosmic fabric. It is a concept that invites contemplation, allowing your thoughts to wander freely, much like clouds drifting across a starry sky, leading us naturally to the next layer of this intricate story. Einstein's relativity and its foundations. As we continue our serene voyage through the cosmos, let's delve deeper into Einstein's theory of relativity, the cornerstone that reshapes our perception of space-time. Picture yourself in a tranquil garden where the flowers bloom not in straight lines but in graceful arcs, influenced by the unseen contours of the ground beneath. Einstein proposed that what we call gravity is merely the curvature of space-time caused by mass and energy, a revelation that transformed physics from a rigid set of rules into a fluid, dynamic dance. In his special relativity, he showed that time is not a constant tick, but varies depending on your speed and the strength of gravity around you, much like how a river's flow slows in deeper waters. This means that if you were to travel near the speed of light, time for you would pass more slowly compared to someone at rest, an idea that evokes a sense of wonder without any urgency. Everyday objects, like a gently swinging pendulum, can illustrate this. As it moves through varying gravitational fields, its rhythm subtly changes, reminding us of spacetime's influence on the world we know. These concepts, while profound, are presented here with the softest touch, allowing you to absorb them at your own pace, feeling the gentle rhythm of the narrative carry you further into relaxation. And as we ponder these foundations, we naturally transition to how space-time affects the very essence of time itself, unfolding like a calm evening breeze. The nature of time in space-time. Building on the elegant curves of Einstein's relativity, let's now reflect on the nature of time within this vast space-time continuum, a concept that flows as smoothly as a lazy stream under a moonlit sky. Time, in the realm of physics, is not the straightforward march we experience in daily life, but a dimension intertwined with space, bending and stretching in response to the universe's grand design. Imagine time as a meandering path through a peaceful forest, where the distance between trees varies, making your journey longer or shorter depending on the route you take. In general relativity, time dilation occurs near massive objects, such as a black hole, where clocks tick more slowly, illustrating how gravity pulls at the fabric of moments themselves. This is not just theoretical, it is observable in our world, like how atomic clocks on satellites run slightly faster than those on Earth due to the weaker gravity in orbit. As you let these ideas settle in your mind, you might feel a deep sense of calm, recognizing that time is both a companion and a mystery, guiding us through the cosmos with gentle persistence. This understanding invites a peaceful introspection, helping you release the day's worries as we ease into the next aspect of our exploration, where the dimensions of space come into play. Dimensions of space within spacetime. From the flowing essence of time, we now turn our attention to the dimensions of space that complete the spacetime puzzle, expanding our view like a soft dawn light revealing a vast landscape. Space, in its simplest form, is the three-dimensional arena we navigate every day: length, width, and height. But when woven into spacetime, it gains a fourth dimension that adds layers of depth and intrigue. Think of it as a serene ocean, where the surface waves represent our everyday movements, but beneath lies an unfathomable depth influenced by hidden currents. In physics, these dimensions are not isolated. They are interconnected, with spacetime's curvature affecting how objects move through them, much like a boat drifting along the contours of the sea. Einstein's equations show that in regions of strong gravity, space itself warps, altering distances and directions in ways that challenge our intuition but inspire a quiet awe. As we contemplate this, you can feel yourself relaxing deeper, the gentle narration acting as a bridge to these cosmic truths, making the abstract feel intimately familiar. This seamless blend of space and time leads us onward to explore how these dimensions curve under the influence of massive bodies, drawing us further into the heart of the universe's elegance. Curvature caused by gravity. As we drift further into the interplay of dimensions, let's consider the curvature of spacetime caused by gravity, a phenomenon that shapes the universe with the subtlety of a whisper in the wind. Gravity, far from being a mere pull, is the result of mass warping the spacetime around it, creating dips and valleys that guide the paths of planets, stars, and even light itself. Visualize a tranquil pond where a stone creates ripples, each wave representing how a massive object like the sun bends spacetime, causing Earth to orbit in a graceful ellipse rather than flying off into the void. This curvature is not just a theoretical construct. It is evident in the way light from distant stars bends around our sun during a solar eclipse, a gentle reminder of the universe's interconnectedness. In Einstein's framework, every object contributes to this cosmic shaping, from the tiniest particle to the largest galaxy, all part of a harmonious whole. As these ideas envelop you, let the soothing rhythm of our story help you unwind, feeling the weight of the day lift away, naturally leading us to the next revelation about gravity's role in the grand design. Gravity is a manifestation of curves. Continuing from the gentle bends we have explored, gravity reveals itself as a manifestation of spacetime's curves, a concept that unfolds like the petals of a flower in the soft morning light. Rather than an invisible force acting at a distance, gravity is simply the geometry of spacetime dictating the motion of objects, much like how a marble rolls along the contours of a gently sloping hill. In this view, massive bodies create depressions in the fabric, and everything else follows the path of least resistance, moving in straight lines through this curved realm. This perspective, born from Einstein's genius, eliminates the need for mysterious forces and replaces them with the pure elegance of geometry, offering a sense of order and beauty that can ease the mind into tranquility. As we ponder how satellites orbit Earth or how galaxies cluster together, you will find these examples grounding the abstract in the familiar, allowing your thoughts to flow freely and peacefully. This understanding paves the way for us to examine more profound phenomena, such as the enigmatic black holes that exemplify spacetime's extremes. Black holes and spacetime warping. With gravity's curves fresh in our minds, let's ease into the fascinating world of black holes, where space-time warping reaches its most dramatic expression, like a deep, still lake absorbing all that surrounds it. A black hole forms when a massive star collapses, creating a point of immense gravity that bends space-time so severely that not even light can escape, drawing everything into its inescapable embrace. Think of it as a cosmic whirlpool where the fabric of reality funnels inward, compressing space and time into an infinitely dense singularity at its core. Around this singularity, an event horizon marks the boundary beyond which no return is possible, a threshold that evokes a quiet sense of mystery rather than fear. Einstein's equations predict these objects, showing how they warp the surrounding spacetime, affecting nearby stars and even the flow of time itself. As we contemplate this, let the gentle pace of our narration cradle you, helping you relax deeper into the night's embrace and guiding us smoothly to the next aspect of these celestial wonders. Wormholes as shortcuts in spacetime. From the intense warping of black holes, we now glide toward the intriguing possibility of wormholes, those hypothetical tunnels through space-time that could serve as shortcuts across the vast cosmos, much like a hidden path in a serene forest leading to unexpected clearings. In the realm of theoretical physics, a wormhole is a bridge connecting two distant points in space-time, potentially allowing travel between them in ways that defy our everyday experience. Imagine folding a piece of paper so that 2 points touch, creating a direct link that bypasses the long route. That is how scientists envision these structures, formed perhaps by the extreme curvature near black holes or through exotic matter that defies gravity. While we have not observed them yet, the mathematics of general relativity suggest they could exist, offering a glimpse into the universe's playful ingenuity. As you let this idea settle in your mind, feel the calm reassurance that these concepts are here to inspire wonder, not disrupt your peace, leading us naturally to explore how time itself is affected by such phenomena. Time dilation in everyday contexts. As we ponder the shortcuts of wormholes, let's shift our focus to time dilation, a direct consequence of space-time's curvature that influences time in subtle, everyday ways, like the slow ticking of a clock in a quiet room. Time dilation occurs when time passes at different rates, depending on gravity and velocity, as Einstein's relativity explains, making it longer or shorter based on your position in the universe. For instance, if you were to climb a tall mountain, your clock would tick slightly faster than one at sea level because of the weaker gravity, a difference so minute it is imperceptible in daily life, but profound in its implications. Think of it as two streams merging, where one flows more swiftly due to a gentler slope, illustrating how our perception of time can vary across the cosmos. This effect is crucial for technologies like GPS, where satellites must account for these discrepancies to provide accurate readings, blending the abstract with the practical in a way that soothes the intellect. As these thoughts weave through your mind, let them carry you deeper into relaxation, transitioning us to more intriguing examples of this phenomenon. The twin paradox explained. Building upon the nuances of time dilation, we arrive at the twin paradox, a thought experiment that highlights the peculiarities of time in a relativistic universe, unfolding like a gentle story told by a fireside. Imagine two identical twins. One stays on Earth while the other embarks on a high-speed space journey, only to return younger than their sibling, a result of the traveler experiencing time more slowly due to their velocity. This paradox is not a contradiction but a demonstration of how space-time treats motion and gravity, with the moving twin aging less because their path through space-time is altered. Einstein's theory resolves this by showing that acceleration and gravity play key roles, ensuring that the universe's rules remain consistent, much like how a river's current varies, but always leads to the sea. As we unpack this puzzle, you will find it invites a peaceful reflection on the passage of time, helping you release any lingering tensions and flow into the next part of our narrative. Space-time and the universe's expansion. From the personal scale of the twin paradox, we expand outward to how space-time influences the universe's grand expansion, a process that began with the Big Bang and continues to this day, like a balloon slowly inflating under a starry sky. According to cosmology, space-time itself is stretching, carrying galaxies away from each other at accelerating speeds, driven by the mysterious force of dark energy. This expansion means that the distances between objects in the universe are increasing over time, altering the fabric in ways that echo the curves we have discussed earlier. Think of it as a vast, breathing entity where every point moves apart, creating more space as time marches on, a concept first inferred from the redshift of distant galaxies. Einstein's equations, particularly with the cosmological constant, help us understand this, revealing a universe that is not static, but dynamically evolving. As you absorb these ideas, let the soothing flow of our words guide you into deeper calm, leading us to the origins of it all. The Big Bang and space-time's origin. As the universe's expansion captivates us, let's trace back to the Big Bang, the singular event that birthed space-time itself, emerging from a state of infinite density like a seed sprouting in the dawn's light. In this theory, all matter, energy, space, and time originated from a rapid expansion about 13.8 billion years ago, unfolding space-time from a pinpoint to the vast expanse we observe today. Before this moment, our current physics suggests there was no before, as time itself began with the Big Bang, a notion that invites a profound sense of wonder and humility. Visualize it as the first breath of the cosmos, where particles and forces separated, allowing the structure of reality to form and evolve. This event set the stage for everything we have explored, from gravity's curves to time's flow, all part of a majestic narrative that soothes the soul. As we linger on this cosmic beginning, feel the peace it brings, drawing us forward to the hidden players in space-time's story. Dark matter's role in space-time. From the fiery birth of the universe, we now consider dark matter, that elusive substance that weaves through space-time, providing the invisible scaffolding for galaxies and clusters, much like unseen roots supporting a mighty tree. Though it does not interact with light, dark matter makes up about 27% of the universe's mass energy, exerting gravitational pull that shapes space-time's curves without emitting any detectable radiation. Scientists infer its presence from the way galaxies rotate faster than visible matter alone could explain, indicating a hidden mass that bends space-time in subtle ways. Think of it as a gentle undercurrent in a river, guiding the flow without breaking the surface, ensuring that structures like our Milky Way hold together against the void. This mysterious component adds layers to our understanding, enhancing the elegance of physics while inviting quiet contemplation. As these ideas settle, let them ease you further, transitioning to the force that accelerates the cosmos. Dark energy and space-time acceleration. Building on dark matter's quiet influence, we turn to dark energy, the enigmatic driver behind space-time's acceleration, expanding the universe at an ever-quickening pace like a sigh that echoes through eternity. Comprising about 68% of the universe's content, dark energy acts as a repulsive force, countering gravity and stretching space-time further apart, a discovery that reshaped cosmology in the late 20th century. Einstein initially introduced a similar idea with his cosmological constant, only to revisit it as observations confirmed the universe's hastening expansion. Imagine it as a subtle wind filling a sail, propelling galaxies away from each other, ensuring that the cosmos continues to grow and evolve. This phenomenon not only explains the fate of the universe, but also highlights the dynamic nature of space-time, offering a canvas for endless reflection. As we ponder this, feel the narrative's rhythm lull you deeper, leading us to the quantum realm. Quantum aspects of space-time. From the large-scale dance of dark energy, we descend to the quantum aspects of space-time, where the fabric reveals its granular nature at the smallest scales, like whispers in a vast hall. In quantum physics, space-time is not a smooth continuum, but might be composed of tiny, fluctuating units, challenging our classical views with probabilities and uncertainties. This idea, explored in theories like quantum gravity, suggests that at the Planck scale, space and time could be discrete, much like pixels in a serene digital image that blend into continuity from afar. Einstein's relativity meets the quantum world in concepts like wormholes at microscopic levels, blending the familiar with the profound in a way that sparks gentle curiosity. As you let these notions wash over you, they serve as a bridge to even more intricate theories, maintaining the calm flow of our journey. Basics of string theory. As we navigate the quantum landscape, let's touch upon the basics of string theory, a framework that envisions space-time through vibrating strings, resonating like soft notes in a cosmic symphony. In this theory, fundamental particles are not points but tiny, looping strings that vibrate in different ways, giving rise to the forces and matter we observe, all within a multidimensional space-time. Rather than the 4 dimensions we are accustomed to, string theory proposes 10 or more, with extra ones curled up tightly, hidden from our perception like folded fabric in a quiet room. This elegant idea unifies quantum mechanics and relativity, offering a potential theory of everything that paints physics as a harmonious melody. As we contemplate these strings, feel the peace they bring, guiding us to the directionality of time. The arrow of time. From the harmonious vibrations of string theory, we reflect on the arrow of time, that one-way flow that gives our universe direction, much like a river steadily making its way to the sea. In physics, time's arrow arises from the second law of thermodynamics, where entropy increases, turning order into disorder and defining the past from the future. This concept explains why we remember yesterday, but not tomorrow, embedded in the structure of space-time as an irreversible process. Think of it as a gentle current that carries us forward, ensuring that events unfold in a predictable sequence, from the Big Bang's heat to the eventual heat-death of the universe. As this idea envelops you, it fosters a deep sense of tranquility, leading us to the relativity of events. Relativity of simultaneity. Continuing with time's flow, we explore the relativity of simultaneity, where what happens now depends on your vantage point in space-time, like different views of a tranquil sunset from various hills. Einstein taught us that simultaneity is relative. Events that seem simultaneous to one observer might occur at different times for another moving at high speed. This insight challenges our intuitive sense of time, but reveals the flexible nature of space-time, ensuring that the laws of physics remain consistent across the cosmos. As we unpack this, imagine two friends waving from speeding trains, their perceptions shifted yet connected, illustrating the universe's intricate web. This gentle revelation paves the way for practical applications in our world. Space-time in GPS technology. From the abstract relativity of events, we ground ourselves in how space-time affects GPS technology, an everyday marvel that relies on precise timing in the curved fabric of reality. Satellites in orbit must account for time dilation due to their speed and the weaker gravity they experience, ensuring that signals reach your device accurately, much like adjusting a clock for a higher altitude. Without these corrections, based on Einstein's theories, your phone's location would drift by kilometers, highlighting how space-time's curves impact modern life. This blend of cosmic principles and practical tools offers a comforting reminder of science's reach, allowing us to appreciate the elegance without strain as we move to more tangible effects. Everyday effects of space-time. As GPS bridges theory and practice, let's consider the everyday effects of space-time, from the subtle shifts in our daily routines to the way it subtly influences our perception of the world. Even in our terrestrial lives, gravitational time dilation means that time passes slightly differently at varying heights, though the difference is imperceptible without precise instruments. Think of it as the Earth itself molding space-time around us, affecting everything from atomic clocks to the aging of astronauts in space. These effects, while minute, underscore the universality of physics, inviting a peaceful acknowledgement of our place in the cosmos. As these ideas resonate, they lead us to the warping caused by massive objects. Space-time warps around massive objects. Delving deeper, we examine how space-time warps around massive objects, creating gravitational wells that dictate the motion of celestial bodies, like a stone creating ripples in a pond. Stars, planets, and galaxies all contribute to this warping, with their mass indenting the fabric and guiding orbits and trajectories in a ballet of precision. Einstein's equations precisely describe these interactions, showing that the closer you are to a massive object, the more pronounced the effects, such as the bending of light during eclipses. This warping is the essence of gravity, a concept that fosters a sense of wonder and calm, transitioning us to familiar analogies. The fabric analogy for space-time. From the warping effects, we return to the fabric analogy for space-time, a simple yet powerful way to visualize these complex ideas, much like a blanket draped over invisible forms. Imagine a rubber sheet stretched taut, where placing weights creates depressions that represent gravitational fields, illustrating how objects follow curved paths through space-time. This analogy helps demystify relativity, making it accessible and reassuring, as if you are unfolding a map of the universe in your mind. As we linger on this image, it provides a foundation for understanding light's journey through this fabric. Light's path through space-time. As the fabric analogy clarifies our view, let's follow the path of light through space-time, where photons travel in straight lines that appear bent due to curvature, like beams in a hall of mirrors. In the absence of gravity, light moves in a straight trajectory, but near massive objects, space-time's warp alters its course, a phenomenon observed in gravitational lensing. This bending allows us to see distant galaxies magnified, offering glimpses of the universe's depths without any abruptness. As light's story unfolds, it highlights the interconnectedness of all things, easing us into the limits of speed. The speed of light limit in space-time. From light's graceful paths, we contemplate the speed of light limit in spacetime, a fundamental constant that caps the universe's fastest possible speed, like a horizon that defines our reach. Nothing can exceed this speed as per relativity because it would require infinite energy, preserving the causal structure of spacetime. This limit ensures that information travels at a finite rate, maintaining the order of events across vast distances. As we reflect on this, it invites a serene acceptance, leading us to hypothetical adventures. Hypothetical time travel in spacetime. Building on speed limits, we venture into hypothetical time travel in spacetime, exploring scenarios where loops or wormholes might allow journeys to the past or future, like dreams of revisiting memories. While not proven, general relativity permits such possibilities under specific conditions, sparking the imagination without overexcitement. This concept, often seen in fiction, roots in real physics, offering a gentle nod to the universe's mysteries. As these ideas fade, they guide us to broader cosmic visions. Multiverse and spacetime variations. From time travel's allure, we expand to the multiverse, where multiple spacetimes might exist in parallel, each with its own rules and histories, like separate bubbles in a foam. In theories like string theory, our universe is one of many, differing in fundamental constants and dimensions, providing a vast canvas for speculation. This idea enriches our understanding, fostering a sense of infinite possibility. As we ponder this, it leads to the constants that shape reality. The cosmological constant in spacetime. As multiverse theories broaden our horizon, we focus on the cosmological constant in spacetime, Einstein's addition that drives the universe's acceleration, like a steady wind in sails. This constant represents the energy of empty space, influencing expansion and the fate of the cosmos. Its value, once a puzzle, now fits observations, adding to the elegance of physics. As this settles, it paves the way for future inquiries. Future research on spacetime. From the constants, we look ahead to future research on spacetime, where new experiments and theories promise to unveil deeper truths, like unfolding petals in spring. Advances in quantum gravity and gravitational wave detection will refine our models, offering fresh insights into the universe's fabric. This ongoing quest maintains the spirit of discovery, wrapped in calm. As we near the end, it transitions to profound implications. Philosophical implications of spacetime. Reflecting on future paths, we consider the philosophical implications of spacetime, questioning reality, free will, and our place in the cosmos, like quiet meditations under stars. This framework challenges us to rethink existence, blending science with introspection. As these thoughts linger, they lead to a final reflection. Conclusion and gentle farewell. Finally, as we wrap our journey through spacetime, let these wonders linger in your mind, a tapestry of elegance that soothes and inspires. We have traversed from the basics to the profound, all to help you find peace and rest. May this knowledge cradle you into dreams, ending our time together on a note of serene tranquility.